Just sniffing. Okay, so we left off last time, kind of looking at the chromatic number of a graph. So let's just recall. We wrote this as chi sub g, and this is the least number of colors that you need to make a proper coloring. So today what we're going to do is look at some upper and lower bounds that you can put on the chromatic number, just based on the different aspects of the structure of the graph. So let's do two lower bounds to start with. Okay, so there's a proposition. So I'll just write it and then I'll have to define some of the notation in it. So for every graph G, we have the following two inequalities. So one says chi G is greater than or equal to omega G, where this is the clique number. So it's the maximum size of a clique in G. And clique, I think we defined like back in like the first week or something, so I'll remind you. A clique is a subgraph that is Kn. So it's like vertices that are all pairwise adjacent to each other. Okay, so that's one lower bound. And then the second one says chi G is greater than or equal to n of G, which is number of vertices, over alpha of G, where alpha of G is the largest size of an independent set. So pairwise not connected vertices. Okay, I'm gonna number these two. So that's 1 and 2. Okay, so go ahead and take a few minutes to prove both of these inequalities, and then we'll discuss why they're true. Okay, are you guys ready to discuss or still thinking? Ready? Okay, so why is the first inequality true? Yeah. Yeah, so since your vertices and your clique are all connected, they require distinct colors. So that means that your chromatic number is going to be at least the size of the clique. Okay, can anyone think of an example to show that this inequality could be strict? Yeah. So that would mean, okay, yeah, so for Kn, this is an equality, right? So when is it a strict inequality? Yeah. Yeah, so here, I'll write the examples though, so. I can show you the one that I thought of. So this was like, if I put like a K4 here, and then I add another vertex over here. Oh no, never mind. That can have the same number of colors.
Okay, you could just do like C5. The largest click there is 2.
Oh yeah. Mhm.
So I'm blinking on the name, but like star second round that we're talking about it on Peterson graph.
The Peterson graph. Yeah, because the largest click there is also a, yeah. Okay, good. And then what about for the other inequality? What's the argument there? Yeah.
Well, the coloring of a graph is basically just a decomposition of it into independent sets. Because every color is an independent, every set of vertices color,
Yeah.
color is an independent set. And you know, the size of all of those is gonna have to be less than alpha of G. And so, yeah, it follows that you can't have like fewer colors than G over alpha of G.
Yeah, exactly. So each color class, which was just like the vertices of one color. So each of these color classes is an independent set. And so it has at most alpha of G, many vertices in it. And then the inequality follows from that. Because every vertex has to fall into some color class, and each one has size at most alpha of G, so the number of them necessary has to be greater than or equal to n over alpha. Okay, good. And then, so we have these two lower bounds. Oh wait, maybe we should do another, no, I think we're good. Okay, so let's do upper bounds now. Okay, so first of all, like one really obvious upper bound is that chi of g has to be less than or equal to n of g, right? Because like worst case scenario, we could just assign a distinct color to every vertex. And it is possible to achieve this bound, right? So with the complete graph, it needs that many colors. So in some sense, this bound is like best possible just in terms of the number of vertices. But we can obtain better bounds by factoring in more information about the structure of the graph into our bound. So I'm gonna write down, and this is how a lot of these upper bounds are gotten, is by just like constructing a coloring that shows you that you can use a certain number of colors. And the way most of these work is by using something called the greedy coloring algorithm, which we've sort of already talked through in examples. So basically, this is going to give us like a way to color a graph, and depending on, there's like some choices involved, and depending upon which choices you can make, you can improve the number of colors that you use. So I'll explain the algorithm. So this is like a greedy coloring algorithm. So this is just going to give us a proper coloring of a graph, but it's not necessarily the best one possible. So you're just going to start by ordering the vertices. And then what you're going to do is color the vertices in order, and just at each step assign like the best possible color. So let's say the colors that we're using are the numbers 1 through n. So I would color V1, color 1, and then I would look at V2. And if it's connected to V1, I cannot use color 1, so then I would use color 2. But if it is not connected, then I could use color 1. So we'll just color the vertices in order. Assigning V sub I the smallest index color not used on its neighbors. So I'm going to do an example so we can just see why this doesn't always give you the best possible result depending upon the vertex order that you pick. So let's look at the path graph P4. So if I order the vertices just in order, then I will get the best possible coloring, right? So let's say my colors are one is blue and red is the second color. So I would go through and I would say, okay, I'm gonna do V1 first, and that gets the color blue. V2 is connected to a blue vertex, so I can't use blue, so I color it red. And then V3 is not connected to a blue vertex, so I'll use the color blue. And then V4, we would again color red. Okay. But if I pick a different order, then I'll run into problems. So okay, so if I have this order instead, so I start by coloring vertex 1 blue. V2, I would color blue. V3, I am now forced to color red. And then V4 is now left over and I have to use a third color. So I'll color that in green. Okay, so the point of this is like, this example is just to illustrate how to do the algorithm, but also just that it is possible to get a best possible coloring, but it's also possible to get a coloring that is not necessarily best possible. Are there questions? Yeah.
This might be a little like, out there. Do you know if there's always like an order and it gives the best possible color using this algorithm?
I think there is, I think that there is always a vertex order that such that this algorithm gives the best possible result. Yeah. Okay, yeah. So like, what does this illustrate? So let's pretend we hadn't done this example. So like this tells me that the chromatic number of the path is less than or equal to 3, right? Because it's like, I have given you a 3 coloring, but you potentially could find something better. So the way a lot of these upper bound proofs are going to work is by showing that there is a way to order the vertices in such a way that the greedy algorithm uses a certain number of colors, and then that tells you that the chromatic number, it could be less than that, but it is at most that value. So let's see an example of such a result. So it says that the chromatic number of a graph is less than or equal to delta of G plus 1, which was, so delta of G, just to recall, this is the maximum possible vertex degree. So I'll give you a few minutes to think about the proof of this. And it uses like basically just an argument involving the greedy algorithm. Okay, did anyone think of an argument for this inequality? Yeah,
It's like, when do we have to add an n plus one color? And it's when n vertices all neighbor the same vertex, and then we have to make that the n plus one color.
mhm.
And so the maximum number of colors you could have is like the largest case of that, which is delta G, and then plus one for the n plus one.
Yeah, exactly. Yeah. So like, let's say we start coloring the vertices with the greedy algorithm. Every vertex has some number of neighbors preceding it. That number is at most delta of G. And so what could happen is, as I'm trying to decide what color to color that vertex, it has delta of G neighbors with distinct colors. That's kind of like worst case scenario. And then I have to use the n plus first color on that vertex, but it can never be worse than that. So, so yeah, I'll write something. So for the proof, so fix an order of the vertices and color using the greedy algorithm. Every vertex has at most delta of G earlier neighbors. So the greedy coloring cannot be forced to use more than delta of G plus one. Okay. So, are there questions about that? Okay, so for which graphs is this an equality? Yeah. Yeah, complete graphs. I wrote down one other one. Can anyone think of another one?
Odd cycles.
Yeah, that was the other one that I had as well. So odd cycles. Yeah, so for odd cycles, the degree everywhere is 2, but then you need 3 colors to color it. Okay, so this this argument, okay, so this gives us like a little bit of an improvement on our earlier bound, but we still didn't really use anything about the vertex order, right? So like potentially you could imagine improving this by factoring in different aspects of the vertices in order to decide which ones should be colored first, as opposed to just coloring them in any random order. So that's what the next proposition is going to do. So for this, we have that chi sub G or chi of G is less than or equal to 1 plus the maximum of the minimum of d sub I and I minus 1. Where, yeah, so what is d sub I? So this is, so I'm gonna list out the vertex degrees in non-increasing order. So D1 is gonna be the biggest one, and go up to DN. G. So basically what this is gonna do is it's gonna say like, okay, let's do the greedy coloring, but I'm gonna put the worst vertices first, the ones with the largest degree, so I get those out of the way. And then I'll color the easier vertices last. Yeah, so okay, yeah, so let's go through that argument. So that's sort of exactly what's gonna happen. So I'm gonna apply the greedy coloring algorithm, and I'm gonna order the vertices in non-increasing order of degree. And then apply the greedy coloring algorithm. Okay, so then what happens? So when we color the vertex V sub I, how many neighbors, how many earlier neighbors does it have? How many earlier neighbors? So it has D sub I neighbors in total, but we've only dealt with I minus 1 vertices already. So it has at most the minimum of D sub I and I minus 1 earlier neighbors. Does that make sense? So like, if we've already done all of its neighbors, then it will have D sub I earlier neighbors. But, or we could have not done its earlier, we could have not done its neighbors already. But also if we've only done, say like we're only at V3, well then there's only at most V2 earlier neighbors. So we'll take the minimum of those two numbers. Are there questions? Okay, so then what can we conclude about what color we might have to assign V sub I? Yeah,
In the worst case scenario, it gets assigned the like ith color, I think. Basically, or the worst case scenario gets assigned like the min di comma I minus 1 plus first color.
yeah. So like, okay, so say we look at these earlier neighbors and these all have used up already the first that many distinct colors, then we would have to assign V sub I a new color. So the worst case scenario is that the color assigned 2 v sub I is at most the 1 plus that number that color. So I'll put parentheses around this. Okay, so then, are there questions about this? So this is kind of like going vertex by vertex. This is what happens. So then, since this holds for each vertex, so if we take, so we want to know like what is the largest color we used over all of these choices, then we need to take the maximum of all of these numbers. So the max over each I of that number is the largest color that could have appeared or that could have been used. And that finishes the proof. Okay, so now I'm going to ask you to give an example where the strategy described in this proof does not give you the best coloring. So give an example where of a G where coloring, so like coloring greedily using the vertex ordering given by the degree does not give you the best possible coloring. Did anyone come up with an example? Yeah,
Isn't there like? Yes, they're all degree two. So you're basically just working at the right degree.
so can you order these so that you're forced to use 4 colors?
Oh,
Yeah. Yeah,
Kind of convoluted, but
yeah,
if you just put like four in a diamond and one, like make a 4 cycle and then connect all of them to one in the center.
okay,
Then like ideally you color the one in the center first, but if you just add two, like, add two kind of floating vertices and connect them to any corner of the diamond and do that like twice, then you'll, or like 3 times, then you'll
oh wait,
do it on 3.
okay, yeah.
Then it'll be like you end up coloring the corners first, even though there's like no actual value to that, because
Mhm.
and then it ends up being like worse. Than if you colored, like you get 3.
Okay, so the
coats,
graph is 3 colorable, but this would force you to use
Uh,
4. Okay, yeah, my example was, my like construction was kind of similar to this, so I said like, let's look at the path P3. So this is 2 colorable, and my strategy is going to be the same thing, is like add leaves to just force you to like color the vertices in the wrong order. So like I added 2 leaves there and 2 leaves there. So now the vertices with largest degree are those 2, and you would color them first. Oh no, wait. Oh no, I don't think this works. Do you need P4?
First example where it's side back.
It doesn't.
what's your,
Okay, so, well, okay, it's sort of up in the air on how you order the 3 things of degree 5 there. But let's just assume you did them like left to right. You'd color the left one, color 1.
Yeah.
The bottom one, color 2.
Yeah.
The right one, also color 1.
Uh-huh. But we could do it in the other. So like, you're right, let's color this.
Yeah.
Oh no, then, yeah.
Exact same thing. For the things. Or well, you only use, my point for the degree 3 stuff is that you only use the first 2 colors, colors 1 and 2. Like, no matter how you order. That means that your center vertex is going to have color 3.
Mhm.
And then you'd, or okay, it's
Oh, but the
also
top,
the top vertex. I think you're not gonna get a 4th color on it, because I think the left and right, no matter how you do it, are gonna end up with the same color. Basically.
Wait, but why does the second one not work if you do like a 4 instead of?
I think the 4, I think you do need the 4. Right, so the right vertex ordering was like first, last, and then middle, middle, so. I think this works. So we would color this vertex blue, this vertex blue. And then the one of the middle vertices would have to be, yeah, I think this works. So this is the coloring that you would get. But the graph is actually bipartite, so you could color it with 2 colors. I think that there's probably a way to fix, to like make this one work, maybe by adding more edges or something.
I think the issue is that so your outer your outer vertices, like, I guess I don't think the cycle graph actually has a bad ordering. Is sort of the issue, is that you want the outer cycle to use 3 colors somehow. You want to add a bunch of edges, the outer cycle ends up using 3 colors, then your center one will use a 4th.
Mhm.
Or alternatively, like, you want like
Oh, right, but as you go around the cycle, you're not gonna be forced to use a
Yeah.
3rd color. I see, yeah. Oh, but maybe, okay. Proposed fix, what if you make it an odd cycle? But then connect the middle vertex to just a choice of 3 of them. Oh wait, I want an odd cycle.
That,
And then add leaves to force the coloring to make these have 3 different colors. So what order do we need to do? First,
I think you
second,
maybe force that like, you force one of the ones that the central point is connected to be the final thing in the cycle. Color.
yeah. So maybe that. Okay, but I think we get the idea that we can like force bad vertex orderings by just appending leaves. And maybe, and yeah, you can probably like just, so yeah, anytime you have a graph at a bad vertex ordering, I think you can force this algorithm to color it badly by just adding leaves and the way they would make the vertices be ordered the right way. Okay, so let's do another upper bound, and this one's gonna be non-constructive, so we won't have like a description of how to color the graph that way. So let's just see how that argument looks. So this is a theorem. So if G is a graph, then we have the following upper bound. So chi G is less than or equal to 1 plus the maximum over subgraphs H of G of the minimum vertex degree in H. Okay, so let's see how this goes. So for the proof, let's let K be chi of G. And I'm gonna let H prime be a K critical subgraph of G. So recall that this means that H has the property that any subgraph of it can be colored with fewer colors.
You know H prime exists.
Yeah, I was just wondering that actually. I don't know. Is there hmm.
Definition of a K critical, it's just every subgraph, it can be colored in fewer than K colors.
Yeah.
I feel like you can probably just construct like, I don't know, like a post set of all the subgraphs of G ordered by inclusion, and it would just like. Because you just need to find like,
So like consider subgraphs of G. If one of them can be colored with K colors, then consider that graph.
yeah, it either has a subgraph that can be, that is like K chromatic, or it doesn't, if it doesn't, you found your K critical subgraph.
Yeah, okay. I find this convincing. So are you convinced or no?
I think.
Okay, so start with your graph G. If it has a graph that can be colored with K colors, a proper subgraph that can be colored with K colors, then consider that graph. and ask the question, does this graph have a subgraph that can be colored with K colors? And keep going, and eventually you have to stop somewhere because the empty graph can be colored with one color. So yeah, somewhere you find like a K critical. You can't just keep deleting edges and still okay, are we on board with this? Are there questions? Okay, so then I'm gonna make a claim, which is that if H is K critical, then delta of H is greater than or equal to K minus 1. So if H is K critical, the minimum vertex degree has to be greater than or equal to K minus 1. So like why this seems random, but like let's think back. So what this is saying is that every vertex has at least K minus 1 neighbors. So if you think about coloring with the greedy algorithm, that would mean that that kind of goes back to that statement that like if all of your neighbors have different colors, then you're going to be forced to use the kth color. So okay, so let's prove this claim. So it was just some intuition to see like why this statement isn't like completely random. So let's let X be a vertex of H. Then since H is K critical, we know that the graph H minus X can be colored with K minus 1 colors. Okay, and then if it were the case that the degree of that vertex in H was less than K minus 1, so if that were the case, then in our K minus 1 coloring of H minus X, we wouldn't have every color appearing, right? So the K minus 1 colors used on H minus X do not all appear in the neighborhood of X. So then I can assign a color not used on N of X to get a proper K minus 1 coloring of H. Okay, so maybe a picture would help. So okay, so let's suppose I have some vertex. Let's fix a K for this picture. So let's say K is 4, just for the the sake of the picture. So then if I have some vertex X with fewer than 3 neighbors, so then X has 2 neighbors. Okay, so here's my graph H. It has this vertex X that only has 2 neighbors in H minus X. And then we're saying that H minus X is 3 colorable. Okay, so let's say it's like an odd cycle or something. Okay, so I delete X and I see that H minus X is 3 colorable, so I color it with 3 colors. Oops. But then that 3 coloring of H minus X gives me a 3 coloring of H because I can just use the color that is not in the neighborhood of X. So there's no blue vertex, so I can color that blue. So this gives me a 3 coloring of H. Which is a contradiction because we wanted H to be K critical. Does that make sense? Other questions? Okay, so that means that for every, so by the claim for every X in H, we have that the degree of X has to be greater than or equal to K minus 1. Okay, so then going back to finishing proving the theorem. So let's recap a little bit because we've gone a little bit astray. So we want to prove this statement, this inequality. And we have, I'm gonna let this just be H. We have a K critical subgraph of G, and we know something about its vertex degrees. Okay, so if I look at the max over subgraphs of G of the quantity delta of H, well, I know, maybe now I should call these H primes. Okay, so now I know that my K critical H is among those subgraphs. So this is, at the very least, this is going to be delta of H, right? Because H is just among these. And I know that delta of H by the claim, delta of H is greater than or equal to K minus 1. Where K was the chromatic number of G. So this is equal to chi of G minus 1. And that finishes the proof of the theorem. So we get chi of G is less than or equal to 1 plus this max over H's in G. Delta H primes in G. So where did this come from? This is by the claim. This is since chi of G is K, and this is just since H is among those in the max. Okay, are there questions about this proof? Okay, so we had earlier an upper bound. So just earlier in this lecture. We had the upper bound, chi of G is less than or equal to 1 plus delta of G. And we saw that this was an equality for complete graphs and odd cycles. But it turns out that these are essentially the only graphs where this is an equality. And the statement of that is a theorem called Brooks' theorem. And the way the proof works is just by picking the vertex ordering more carefully in when we color the vertices. So I'll write the statement and then maybe I'll make a comment about why it's useful. So here's the theorem. And this is called Brooks' theorem. And it says if G is a connected graph, other than a complete graph or an odd cycle, then this above inequality becomes strict. So now chi of G is less than or equal to delta of G. Okay, so for example, why is this useful? So I can conclude that the Peterson graph is 3 colorable now just by looking at this statement and not even having to produce a 3 coloring of it. So yeah, so this can give you some, so if we wanted to know, say we didn't already know what the chromatic number of the Peterson graph was, I just handed you this graph. Now you have 2 results. You know that the chromatic number has to be less than or equal to the maximum vertex degree, which is 3. So we know that it's 3 colorable, and we also know that it's not 2 colorable because it has an odd cycle in it. So yeah, so these theorems are pretty useful because without really having to delve too much into finding a coloring, which could be quite complicated and there's a lot of possibilities, we can make conclusions about what the chromatic number is. So, I need to plug in my laptop. Okay, so let's go ahead and prove this theorem. So for the proof, I'm gonna let G be a connected graph. And I'm gonna let K denote the maximum vertex degree in G. And we can already do away with the cases when K is 1 and when K is 2. So let's think quickly about why the theorem already holds in these two cases. So what happens if K is 1?
That's like C is missing.
Yeah, so this is the only possible graph. So why is the theorem true for this graph? Yeah,
It's too colorable. Oh wait, sorry.
so this is kind of a trick question. It's excluded from the theorem because it's a complete graph. So yeah, so this is K2. So it's excluded from the state. It's like, yeah. Okay, and then what if it K is 2? Yeah,
It's either gonna be a path or a cycle, and we know that those either have two colorings or are odd cycles and excluded from the theorem.
yeah, so right, so if your maximum vertex degree is at most 2, so every vertex either has 1 or degree 1 or 2, then you're either a path or a cycle, which is either too colorable or it's an odd cycle. So it's excluded. Okay, so we're gonna assume that K is at least 3 for the rest of the proof. Okay, so our goal is going to be to order the vertices so that each vertex has at most K minus 1 lower indexed neighbors. So our goal is going to be to order the vertices so that each one has at most K minus 1 lower indexed neighbors. Right, because if you had a vertex and all of its k neighbors were lower index, then you'd be forced to use a k plus first color. Or you could be forced to use a k plus first color. So, so this is our goal. Does it make sense why we want to do this? So if we do this, then we have a k coloring. So yeah, if we do this, the greedy coloring, we'll use k colors, or at most k colors. Okay, so that's the goal. If we do this, then we win. So there's a few cases. So the first case that is considered in the proof is, let's suppose G is not K regular. So then what we're going to do is choose a vertex of degree less than K as the last vertex Vn. Okay, so then how do we order the rest of the vertices? So since G is connected, I can grow a spanning tree from this Vn, and I'll assign indices in decreasing order as they're reached by this spanning tree. Okay, so maybe I'll draw an example. Maybe the Peterson graph is just oh no, but that's K regular. I'll do the Peterson graph minus an edge as the example. Okay, so it has 10 vertices, so I'm going to pick this one to be V10. And then I'm going to start growing a spanning tree out and just assign the numbers as this happens. So we have V9, V8, V7, V6, V5, V4, V3, V2, and V1. Okay, so why does this vertex ordering achieve our goal? So why does this vertex ordering have this property that each vertex has at most k minus 1 lower index neighbors? Yeah, no, yeah. You look a little like,
Oh, no, wait, more index neighbors, actually. Let me think about that again, yeah. Oh, I was gonna talk about higher index neighbors.
No, but I think that's a good, so what do you know about the higher index neighbors?
This is their.
Yeah. Yeah, so each one, right, so we started here and then we started going down, right? So each vertex has one higher index neighbor, right? Like this one has a higher index neighbor. But we also know that the maximum vertex degree is k. So that means that we have, looking at the lower index neighbors, there's at most k minus one of them. Right, because we already used one of the neighbors as a higher index one. Making sense, so. So each vertex other than Vn has a higher index neighbor so each one has at most k minus one lower index neighbors. And that statement is true also for Vn because Vn already was assumed to be a vertex that had degree less than k. Okay, are there questions about this case? Okay, so there's three cases. So now we get into like the k regular ones, and then that breaks down into two, which is if it has a cut vertex and if it does not have a cut vertex. So I think we're only gonna have time for the case when the graph is k regular and has a cut vertex, but the last remaining case is written in the book if you're interested. So for two, we'll assume that G is k regular. And it has a cut vertex. Okay, so I'm gonna let G prime be a subgraph consisting of a component of G minus X together with the edges that go to X. So let's let G prime be a subgraph consisting of a component of G minus X together with the edges to X. So, okay, yeah, I'll draw a picture. So let's say here's our cut vertex. I always I have such a hard time drawing regular graph examples. Okay, so here's X. Okay, so let's say this is our graph G. You know what, I'm just gonna make both sides of this the same. So it actually is k regular. So then, for example, what is G prime? Like this could be my G prime.
I think this graph is not clear.
Oh no, because X is no. Okay, I don't think it's gonna matter. Let's pretend that it is irregular and hope that the example is like satisfactory for illustrating the idea. Oh God, can I just add vertices to make each of these, or add edges to make them?
Yeah, very similar.
Really making
It's like for, yeah.
okay, yeah. Okay, let's hope that this example is satisfactory, even though it doesn't actually satisfy the condition. So this is my subgraph G prime. So so the degree of X in G prime is less than K. And so the method used in part 1 will give me a K coloring of G prime. So let me write that down. The degree of X in G prime is less than K. So the method from case 1 will give a K coloring of G prime. Okay, so then that gives me a K coloring of G prime. I can do the same thing to get a K coloring of the left half of the graph. And then potentially by just switching around which color is which, I just make them agree on X to get a K coloring of the whole thing. So do the same. I'm rushing this because class is over, but we'll do the same for the left. And then this gives us a K coloring of G, just by, possibly you might have to switch red and blue in one half or something to just get agreement on the middle vertex. Okay, so that's the end of class today, and I'll see you all next week or in office hours today.